The second question, number 7, asks something similar, except now the water is surrounding this prism rather than air, so the refractive index is 1.33, and the request is the same, to finish the ray diagram and indicate all the angles. So let's go to a drawing here, and it's just like the other one. It is the special case where you have a incident ray that is perpendicular to the interface, and so that transmitted wave will go directly in like this. That we give you a 45-degree angle here and a reflected 45-degree angle here, right there. Intersecting this interface, the same thing, 45-degree angle. Right now I'm only paying attention to what's happening inside the prism. So the question will be, what happens when the ray exits, or if it does exit the prism and enters this space, which has a refractive index of 1.33. Now notice we're ignoring all these things about, the difference in the refractive index and whether or not the reflected beam is inverted, etc. That really is only a concern for us when we're doing thin films and we're looking at interference. Now we're doing sort of macroscopic things with, large chunks of glass, and we're not really worried about the coherence of the wave. We're worried about how the ray is traveling inside this relatively large object, large compared to the size of the wavelength of light. Okay, so here is the angle that we have, this theta here, theta 1, and then there's another angle made by the exiting ray, theta 2. Now, we're going to use Pete's idea of this car where you have wheels. So we know when this car comes up, the first wheel to touch or enter through the other material is the left front one. The refractive index is lower than where it's been traveling. Therefore, it will cause it to turn in that direction. It sort of slips. It can go faster. So there you will get a ray that is making this angle just like the other case we did, making it larger. Same thing here. The wheels to first touch will be these front ones here as it hits here, and the refractive index is lower, so it will cause it to turn that way, and so the ray will, here's the angle theta, it will actually increase the angle here, so go like that. Okay, so the angle we're looking for is theta 2. And using Snell's law, n1 sine theta 1 equals n2 sine theta 2. And in this case, we have 1.33 times sine theta 2. And we have 1.5 times sine 45. So 1.5 over 1.4 roughly, 1.414 equals 1.33 times the sine of theta 2. Bring this over, 1.5 over 1.4 times 1. I'm going to call this 4/3. I'm going to put 4 on the bottom, 3 on the top. So what I'm doing is 1.33 is equal to 4/3, and turning that into a fraction. So 1.5 times 3 is equal to 4.5 divided by 4 times 1.4 equals sine of theta 2. So now I'm just in a mode of approximating. 4.5 divided by 4 is approximately 1.13. So I'm rewriting this over here. 1.13 over 1.4 equals the sine of theta 2. Okay, so close enough. 1.1 over 1.4. Ooh, so if I were to draw a triangle, what angle would that be? So roughly 11 over 14. 11 over, so the sine of an angle something being 14 long, and this guy being 11 long. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 long and 14. So let's see, that would take 11, 12, 13, 14. So I'm going to kind of draw a circle of this radius out here. Where would 14 be? Ooh, kind of over there. So, is that right? It would even be a little bit further. So the angle is going to be a little bit like this. So this angle right here, I don't know. I'm going to say it's about a 60 degrees. 60 degrees. Theta 2 is about 60 degrees. I'm estimating the sine value here. So what I have calculated is that theta 2 is about 60 degrees. Same thing here. Say theta 2 is about 60 degrees.